I have 3 examples online. I think I posted the PowerPoints, so you're welcome to go through the PowerPoints and go through all the linear equations. They become cookie cutter after a while. They're a procedure. The Chinese remainder theorem is on page 39. That's where we are at now. I'm trying to, what I feel like going through the number theory book is that the examples are getting more condensed, and the theorems are there, but it's just really hard to extract out. So I'm going to other sources to kind of give you a more full picture. What the Chinese remainder theorem is used for is it's used for finding solutions of simultaneous equations of linear congruences. Because if you remember, when you started out algebra, you were solving linear, just one linear equation, like 3x equals 5. That's where we were in the previous lecture. The next step you took, a leap a little while later, is to solve simultaneous equations where you're looking for one solution for the simultaneous system of equations. And that's where the Chinese remainder theorem is applied. So for example, I took this example from a YouTube video. We have x congruent to 2 mod 3, x congruent to 2 mod 4, and x congruent to 1 mod 5. So really what you're looking at in this system, what you're looking for is each one of those systems represents a box of numbers. You're looking for the intersection of those boxes that satisfies all 3 of those equations. So you're looking for the numbers that are actually at the intersection of all those 3 boxes. So I'm going to give you this step by step. We were talking about this the other day. You and I were talking this. I think like that. I can actually take anything that I do. Sometimes I don't think like that when I'm putting things together, but when I'm trying to explain it, I always break it down into steps. And I do this not just for my lectures here, but you can actually pull down some of my very theoretical papers online and see that I sometimes explain my proofs step by step, because then the reviewer can go through and just get through things quickly. The first step, if you're going to go through this procedure of solving this system of congruence equations, is to check that all the pairwise modulos are relatively prime. Those are the modulos I'm talking about, 3, 4, and 5. And indeed, they are all relatively prime. So in the Chinese remainder theorem, this is a checkability thing. You have to start with that, make sure it's satisfied, and then you can apply the theorem. So that's the first step. Well, you don't have to, right? Because it's pairwise. So I always forget. It's looking at the greatest common divisor of 4 and 5 is the same thing as looking at the greatest common divisor of 5 and 4. So you only have 3 things left to look at. Some of you are in combinatorics, right? So you're doing this. So that's checked. Then the way I'm going to show you is the way that was showed on this YouTube video, which I thought was kind of cool, but I adopted it the way so it's kind of digestible for us. So the first thing is to set up the frame of the solution. So what I mean by frame is set up a little table. Your solution is going to be the sum of 3 pieces. So set up a little table where you have mod 3, mod 4, mod 5 linked up with plus signs in between, because you're going to do some addition. So as it unfolds, you'll see this unfold. And when you're taking notes, it's actually easy. I'm writing out the steps, but you're going to just deface your table as you go along. JD, good? We're fine? Okay. See, pen's still moving, pencil's still moving. Okay, the third thing you want to do is put in what we call zap out terms. What I mean by that is, if I go to, let me use my mouse, this column here, I'm looking at mod 3. If I put a 3 here, it will not affect mod 3 because 3 is 0 in the world of mod 3. Likewise, 3 is 0 here in the world of mod 3. So that's what I call zap out terms, because if I mess with the first column, as long as I adjust the other ones mod 3, it's not going to really affect anything. Yeah, you're gonna see it as it unfolds, right? So be patient. I'm constructing the solution, so you're gonna see it. So likewise, you're gonna go and say, what do I have to zap out of the other terms to make sure that whatever I do to the second column doesn't affect the other two, and I have to zap out by mod 4. Same thing here. If I want to do something to mod 5, but I want it not to affect the other two columns, I would have to put a 5 in there. So all I'm doing in these terms is making sure that I'm leveling everything so that when I start messing with each individual column, it doesn't affect the other pieces. So I just wrote what those numbers are. And if you want to, you can just write on the next line of your little table that you made so it's clear where it came from. So I wrote the congruence equations down at the bottom. So I'm going to evaluate what I have with each mod and adjust. So I'm constructing this from the ground up. So I'm going to start with x congruent to 2 mod 3. If I put it, this one's already satisfied, right? Because if I have a 2 in the first column, the first one is x, that satisfies x is congruent to 2 mod 3, and the other ones remain 0. Let me continue on so it makes sense. So now I'm going to move over to the mod 5 one. In the mod 5 one, if I take 12 and mod it by 5, I get a 2. So backing up here, if I took 20 and mod it by 3, I got a 2, right? And that satisfies the first equation. So that's all I'm doing. I'm just looking at that number that's already in the column and seeing what I have to adjust it by. So I don't have to adjust anything in the first column. It satisfies the first equation. And the other ones blot out to 0. So I'm fine. I haven't done it. I don't need to do anything. But if I go to the last column and do mod 5, 12 mod 5 is 2, because the remainder when I take 12 and divide it by 5 is 2. And the equation I need to satisfy is x is congruent to 1 mod 5. So that's a problem. I need that to be a 1, not a 2, in order to satisfy the last equation. You see where I'm going? I'm just building it up piece by piece. And that's where I got the 1 from. So that last equation's not satisfied with what I have in that column at the moment. So what can I multiply 2 by to make that remainder 1? Because I need it to be a 1. 3. Well, I guess I went 6, 7, 8 for some reason. I don't know why. I don't know what I was thinking, but it'll work, right? Once you mod out, it'll work. So I just checked. What happens if I do a 6? It gives me a remainder 2. What happens if I do a 7? It gives me a remainder 4. What happens if I do an 8? Then I have a remainder of 1. So I can change 8 to be the number below 5. 8 is really 3 mod 5. So I'm going to use that 3 instead of the 8. So I'm working in the world of modding 5. So now that tells me that I really need to take that last term, which was 12, and multiply it by 3. Which is what you told me. So now that one is satisfied, right? Now my new adjustment. I didn't have to do anything to the first column, but I had to reconstruct that last column. And I had to multiply that last column by 3 to make sure that that works. Now 36 mod 5, what do I get? 1. So now the last equation is satisfied by that adjustment. Dania, you had a question?
Yeah. Why did you multiply that by 3?
Okay, so backing up right here. So this is my first pass of the solution, right? This column was okay. It satisfies the first equation, and it didn't matter what the other, because they were 0, right? So I went to the last column next because it was easier to work with. So I looked at 12, and I said, well, 12 mod 5 is 2, but I need it to be 1. So what do I have to multiply 2 by in order to make that be 1? And the answer was 3. So I'm going to take that first pass thing that I have here. I can't work with a 2 because I set this all up so that all the other ones will zap out, and I don't want to affect it. So whatever I do here, I don't have to worry about the other columns because they're already zapped out to 0. So I can mess with this column by itself and not have it affect the other columns. And that puts a 3 there, as you found out. And when I do that, I get a result of 36, which now I can look at my adjusted term, and indeed, 36 mod 5 is 1. So now I've got it. Okay, question?
What did the 8 have to do with 4? Yeah, that's not the connection.
You can start, that's the nice part. You can start anywhere in the integers because everything keeps repeating. So for some reason, I just started at 6. I have no idea why, but you could have started with 1, 2, 3. You just need something to give you a remainder of 1 when you mod by 5, right? So, oh, 8 is 3. They're one and the same thing, right? When you mod by 5, 8 and 3 are the same thing, right? And honestly, this is just because this was the pure mathematics I used to do. So I'm so used to just revolving around the door. So I know nothing matters. I can start anywhere I want. I can make all kinds of sign errors. Nothing matters. So when I start with 6, 7, and 8, I will get the same answers if I started with 1, 2, and 3. And I did, right? You said 3 right by looking. I started with 6. I got 3 just by doing it the hard way. Okay.
Row on the other one?
Say that again?
Keep it as 2.
Like that.
You write in new, like,
Oh, this is just my scratch work underneath it. All the red stuff underneath is just my scratch work. This is my real answer that's coming up at the top. So what I'm doing is I'm building up the solution, and this is just my scratch work underneath so I can do my multiplications out.
maybe a little bit of an how did you get, you see the second equation, you x is going to be 2 mod 4. We have to check the
Yeah, we're going there. We're going there next. So now we're going to go to the second column. Right now we know everything's adjusted. We got the 0. It's not really 2 anymore. Because when I go to the world of mod 4, what's 36 mod 4? I don't write 0. So those two don't matter. I'm not going to mess with the center one. Okay, so now that's 15. 15 mod 4 is 3. So this is what I have. But I need it to be 2. So I need 2 there, not a 3. So what can I multiply 3 by to get 2 mod 4? And this time I went judiciously with 1, 2. So I started out with 1. I got 3, which is not right. I did 2 and I got 6, which is indeed 2 mod 4. So I need to take the 3 and multiply it by 2 in order to get 2 mod 4. So the answer is 2. So I need to take that 15 and adjust it by a factor of 2. And now the third equation is satisfied. So that tells me the numbers in each column so that all 3 equations are satisfied. So check. Is each equation satisfied by that sum? I can just sum them up. 20 plus 30 is 50. Add 36, I get 86. Or, yeah, 86. Why did it become 84? Yeah, here it is. It's 86. So here's 86. Minus 2 is 84. Is 84 divisible by 3? Yes. Is each equation satisfied by this number 86? 86 is my answer, right? So I'm going through and checking one by one on each one of these equations. Right. We're getting to that point, right, where we're using the congruence definition as quickly, like 86 minus 2 divided by 3. Is that an... 86 is the sum of all these 3 numbers. So now I'm going to add them. So I've constructed the solution. Add them up, I get 86. 86 is my candidate for the solution that satisfies all 3 equations simultaneously. So I'm checking, does 86 work on the first equation? Answer is yes.
Does it matter what order you go in? So I know when you were testing it first, you
No.
did, okay.
No.
Okay.
.86 minus 2 on that side, on the second equation, is 84. 84 is also divisible by 4. I checked on a big TI-84. It works. And then the last equation is, right, so it works. So 85 is divisible by 5, and so 86, the complete answer is 86. But what mod am I working in? I'm working in mod 60. And I'm going to scale it back down. 86 is larger than 60, so I need to look at the remainder when I take 86 divided by 60, and that's 26. So it's a procedure. And I've never seen it explained that way, but once I saw it on that YouTube video, I thought, oh, that's actually really cool, because usually it feels like it's voodoo. It comes out of the air somewhere, but it's a constructive thing where you're looking at what do I have to build up each one of the terms by in order to get all these three equations satisfied. Well, to do that judiciously, you'll want to make sure that when you're messing with one equation, you're not touching the other two. And that's the first step, to make sure that you have something in line that when you start messing with that one side, it doesn't affect the other ones. 86 is larger than 60. So you just remainder, right? You'll see me do that all the time. We're just rotating back to we're reducing. It's just like reducing fractions. Here's a formal statement of the Chinese remainder theorem from your book. If I have a system of congruences, they're of this form. It's exactly the abstract version of what you just saw with numbers, where I know that this is the checkability thing. The first thing I have to check is that all these are pairwise relatively prime. Then it's going to have a unique solution, mod M1 times M2 times. It's exactly what we found at the very end of that procedure. That's a statement. It has a unique solution. Nice theorem, but how do you construct it? How do you actually find it? That was the previous. I started backwards. I showed you how to construct it first, and then I stated the theorem. And I've never done it that way. I've actually always given the theorem first, prove the theorem, and then try to construct a solution. And everybody was really confused. So I hope this is better, seeing it the other way around. You can't talk to my previous number theory class because they graduated and have jobs now. But I can tell you they were looking at me. What is this about? And I think that in your book, I might be wrong, but I don't recall that I saw a construction of a solution in there. That might have been why I went to YouTube to see if someone was doing it better than I have done in the past. Can I look at, JD, can I look at your book? I'm pretty sure that there isn't an example in the book. Nope, there isn't. So strange. Yeah, I don't know why they don't. Because that's the hard part, right? How do you go actually do one of the problems? So here's your homework. I'm just giving you 2 homework problems that are identical to the procedure that I just started out with. You should be able to look off the YouTube video that I'm going to post where I'm going through step by step. So when I set up the problem, I didn't use vocabulary to put it through. I kind of just said, this is what I'm doing here, this is what I'm doing here, and here's why. So hopefully that's good enough for you to understand how to put things in place and come up with a solution. You can always check your work like I did and make sure that all 3 equations are satisfied by your end result. I don't know really how you would. I mean, you're perfectly welcome to pitch ideas back to me and say, look, you could have said this right here. I'm not quite sure how you would. You know, when we were spinning out the problem forward, all of you are like, what is she doing? Why is there a plus sign in between? And then you saw it enveloping and starting to fall into place. So how do you, I wasn't quite sure how you explain it from the back end.
So next week's quiz is
Yes.
okay.
So it's nice. You're